So today we continue with the remaining part of the routing protocols, and we were discussing these three routing protocols we are to discuss. The RIP, Open Shortest Path First, OSFP, and OSPF, and then Border Gateway Protocol. So we have covered some things from routing information protocol, and we came to know that it is using. You can hear me, alle? You can hear me? Yes, no? Slide കാണാവോ? കേൾക്കാൻ പറ്റുന്നുണ്ടോ? Right. So we'll see that say this two of the first two of them are intra-domain routing protocols, that is within the autonomous system. These are used. Then RIP is having some limitations because it is suitable for autonomous systems which it uses hop count basically as the cost measure. Okay, so because of that, and it's limited, the hops, the maximum number of hops is limited to 15. So you could use it only in small autonomous systems, say autonomous systems whose diameter is within 15 hops. And one thing to note here is that from the source node to the source router, you don't count it as a hop. All the protocols don't count this as a hop. Source node, that is from your PC to your immediate router, you don't count it as a node. You don't take the case of the home router, rather router outside in your ISP. So that's not counted as a hop. Then open, so RIP is converging slower compared to OSPF. We'll see why is it. Then when we come to border gateway protocols, we see that the border gateway protocols will operate at two levels. One which operates at the edge of the autonomous systems, that is what we call as exterior border gateway protocol, and some protocol which runs within the autonomous system, you call it as interior border gateway protocol. So within the autonomous system, the routers will be running either one of these two protocols, RIP or OSPF, plus an interior border gateway protocol. And at the edge routers, the border routers will be running exterior border gateway protocol and an interior border gateway protocol, and then either of these things. So three things will be running, three protocols will be running in the edge routers or border routers. We discussed what are edge routers, all those things. നമ്മൾ അങ്ങനെ കാര്യങ്ങളൊക്കെ പറഞ്ഞായിരുന്നു. എഡ്ജ് റൂട്ടേഴ്സിൻ്റെ കാര്യമൊക്കെ ഡിസ്കസ് ചെയ്തായിരുന്നു. വാട്ട് ഇസ് ആൻ എഡ്ജ് റൂട്ടർ? ഇഫ് യു റിമെമ്പർ ദ ഫസ്റ്റ് സ്ലൈഡ്സ്, we had discussed something called as the core routers, edge routers, right? Edge routers, these are edge routers. So Juniper networks in your edge routers are ഇവിടെ കാണിച്ചിരിക്കുന്നത്. So this is a core routers. So this will be the large backbone networks like use ചെയ്യുന്നതായിരിക്കും. So that is go to slide number 40, right? That also did not get me there, right? So yeah, so we saw that it is based on distance vector. RIP, routing information protocol, is based on distance vector routing. Maximum hop is 15, hop count is limited to 15, then 16 is considered as infinity. This hop is not counted, that is the source node to the source router is not counted as a hop. That also was seen. Then how you advertise the routes, you have to periodically exchange information with its neighbors. Each router will exchange information with its neighbors, whatever it knows about the entire network. So that's how you update the routing tables. Each router will update the routing tables. Now there are some conditions which are put while updating, making these updates. That also we saw. Another thing we saw is that these are using UDP. UDP is a transport layer protocol. So RIP is running the application layer as a process. It makes a UDP. It sends its payload as to the transport layer. Transport layer encapsulates it in a UDP datagram, and passes on to the network layer, which encapsulates it in a IPv datagram, IP datagram. So that is the approach. So port 520. Now two types of messages also we saw: response message and update messages. Okay, update messages could be requested or they could be unsolicited. Okay, so you could it could be in response to an request, or it could be just sent like that. Every 25 to 30 seconds it is sent. RIP message format. So this is the network which we discussed. We have through to 4 routers, 1, 2, 3 and 4. So you are discussing about how initially when it boots up. So all these routers don't boot up at the same time, rather they boot up asynchronously. You can tell it like that, asynchronously. And once they boot up, they try to get information about the network. So they will send some request message to immediate routers in its neighbors. So they will just pass on their forwarding table to this guy. So for instance, R1 boots up, it gets updates from R2. So R3 also get updates. So at periodic intervals there is an update. Also the entry will time out in routers. We'll see that there is an expiration timer for each entry. You can set it. The router admin can set that timer. I think it's in 180 seconds time. That's maximum. You will have to update the route. So all these processes happen concurrently within the routing system. So plus the other routing processes, all those things are happening. So router is basically a very high-end system. You can't use your normal system for that. So it has to deal with those many computations for forwarding the packets, all those things. So when we take up a MPLS, multi-protocol layer switching, we see some other feature which is added on to this, which is a shortcut like thing. You tag the things, tag the traffic. That is one thing for MPLS. So anyway, this is the old routing table of R1. It gets updates. It adds new entries. If it doesn't have any entry, it will add to this new routing table, forwarding table. The old entries are retained. Now, if the new thing is seen by R1, new routing table seen by R1 is, R2's routing table contains new entries, it is added. If it is containing an entry which is of higher cost, and when the next router is the same, means still it will be added, because maybe R1 takes an assumption that it is having a higher cost, because the sending router might have a better idea about the cost involved, because sometimes the link might have changed, some of the links might have failed. So these three conditions do apply, that is when you update the routes. So it will select the new routes as the new routes only in these conditions. That is, else it will retain the old routes, whatever was existing in the old routes. So if so it doesn't exist, it will be added. The received cost is lower than the cost of the old route, it will be added. The new route will be added. The other one, if it is a received route is having a higher cost and it contains a next immediate router, next router is the same. ഈ ഒരു സിറ്റുവേഷൻ വരുന്നതെന്ന് വെച്ചാൽ R2 ആയിട്ട് for if you take this network, say for instance the cost involved to reach this network is I'll say this is what would be the cost involved to reach this network. Say you will say this is 1 hop, 2 hop, so this is not the network, right? Say to reach this network, this is 1, 2, 3, so N5, 3 is the cost. Now all on a sudden this link breaks. R2 gets an update about this. It says its update is its cost. It says to reach N5 you will have to make a hop like this: 1, then 2, 3, 4, I don't think that is will be a valid thing. That is 1, 2, 3. So so this is the cost is given as a higher cost rather than the earlier cost. It's a higher cost comes up, so that has to be updated because this link has failed. R2 is getting a better idea of this. That is why the third condition is imposed. So if the receive route has a higher cost, means still it has to be retained because maybe the these are things to prevent this two node instability. Because two node instability basically involves the least cost propagating faster but the higher cost propagating slower. So any link failures will be updated very it takes several updates to get several updates to be reflected in the routing tables. To prevent that, you use such a strategy, the last one. Now there are 3 timers. This is just like the garbage. I don't usually put slides like this, but I just wanted to fit all these things in the same thing. And there is every 25 or 35 seconds there is update sent. So it will update its it will send its updates. These are unsolicited updates, unsolicited responses. So that is it will send its routing table to its immediate neighbors. Expiration timer, the admin can set the expiration of the route. So when you have an entry, a route entry made in a routing table, you can set the timer. By default, you can say every 180 seconds it will expire. So when there is after 180 seconds the route is considered expired and you will put a 16, that is it's unreachable. Then you need to get an update to update the routing table. You can send either a greeting message to get an update. Like that, the process is always happening. So the router needs to get the best latest information. That's why such a strategy is done. So it means every 180 seconds it has to update that route. Again, the update, even if you discard that route, it doesn't immediately purge it from the routing table. Rather, it will just add a flag sort. So you'll turn on a garbage timer. So you'll put a value of 16 and then maintain it there for 120 seconds. Hello.
അല്ല സാർ ഇപ്പൊ 50 സെക്കൻഡ് സ്ലൈഡിൽ ഏത് സ്ലൈഡിലാണ്? ഞങ്ങളിപ്പോൾ 50th സ്ലൈഡാണ് കാണുന്നത്.
ആണോ? ഓഹോ, ഐ ഡോണ്ട് റൈറ്റ്. എന്താണ് 50th സ്ലൈഡിലുള്ളത്? ഐ ഡോണ്ട് ഹാവ് ദ സ്ലൈഡ്.
റൂട്ടറുടെ
പടമാണ് കാണുന്നത് അല്ലേ? മാറ്റിയായിരുന്നു. ഇപ്പൊ കാണുന്ന സ്ലൈഡ് എന്താണാവോ? ഇപ്പോ ടൈമേഴ്സിന്റെ സ്ലൈഡ് വന്നു അല്ലേ? I don't know. I didn't escape the presentation, still something. I don't know. Anyway, so every 120 seconds it will retain it for 120 more seconds and then it will just purge. So 180 plus 120, that is the retaining period of a route. So that it will retain for this value of infinity, unreachable value for 120 more seconds, so that its neighbors will become aware that there is such a thing. So remember that in the parallelly a process of sending this update to neighbors is also happening. So these are happening concurrently, these 3 processes, and all these routes are not expiring at the same time. Ella 180 seconds ഒരുമിച്ചല്ല expire ആവുന്നത്. For instance, you have 10 routes, they will be, maybe 3 of them will be expiring, rest 7 are there active. So so the routing, the expired routes will be set as 16 and then the update might be sent, say maybe after in this duration, say 31st second it is sent as an update. So these are concurrent processes, these are happening parallelly, right, simultaneously. Now regarding the pros. The advantages of RIP is that this is a simple protocol. You don't involve this exchange of link state packets or anything like that. But the problem, so you don't have a lot of traffic related to routing table updates. Link state packets and link state database updates are creating much traffic. We see later in this open shortest path first. So then it's slower. It's the convergence of routing tables is slower. The updates, all these process takes time. Count to infinity problem is there. That is two node instability. So such things there. So then always there is a issue of misinformation. Each router will depend on its neighbor to get updates about its routes. So always it has to rely on its neighbors. You have to trust its neighbors to get the correct information. So so malicious routers might be there, which can poison the routing table. And so the ISPs have to be careful about that. The competitors might do such tricks. So always there are strategies. There are other levels of making this sort of checks. So that is not a discussion here, but simply said, such a possibility exists, and there are alternatives to. There are measures to counter these things, because we are learning only a part of this topic. That's why we are not getting the full picture of this. Such a possibility does exist, but there are measures to counter it. You can read more about that in books or online. There are different resources. So then we take up the next routing information, next protocol, which is called as open shortest path first. So this is an open protocol. Open in the sense it is an open source protocol, and this is showing the cost for an example. Still, you don't consider this link as a cost. The source node to the source router is not considered as a cost. So you will just say this cost to reach, that is from router R1 to network 4, you take the cost as this is 4, okay, 12, right, is 5 plus 12, right, 5 plus 3 plus 4, that is 12 ആണ് cost വരുന്നത്. That is this hop is 5, this hop is 3, and this hop is 4. So that's 12. That's the cost from router R1 to what do you say, from N1 to N4. That's the cost. Same way you computed the cost. So here the cost, how you assign is that it is unlike routing information protocol where you set it as the hop count. Here it's based on different parameters. So you can consider the traffic, you can consider the security, reliability. All those things can be assigned by the admin. The admin can even simply set as the hop count as a cost. That is also possible. So that in that case it will become similar to routing information protocol because the same metric will be used. As there could be several strategies adopted to set the cost. So unlike this, and this open shortest path first doesn't restrict itself to 15 hops like RIP. RIP has a limitation of 15 hops. Here that such a restriction is not there. It's supporting variable length autonomous systems. So the forwarding table. So we remember this guy Dijkstra who computed this least cost tree. So you need to compute this using Dijkstra's algorithm. Every router has to compute the if you recollect, I'll just I don't right, I think it's 18, right, distance vector. If you remember, yeah, this is the Dijkstra, the guy Dijkstra, and this um, what is done is that you have to build up a link state database, LSDB. So, and every node needs to have a copy of this link state database. That is a key idea there. So, this link state database has to be built up using something which is called as the link state packets. And once each router builds up this link state packets, it will just flood the entire network with this link state packets. So you will just not send it to its neighbors, rather it will send it to every router in the internet other than itself. That's what we call as a flooding. So it sends to every other router other than itself. So that is the issue in link state routing, because you will create a voluminous amount of traffic because of this link state packets. So coming back to this we saw earlier. So right. I think you are seeing the open shortest path first slide, right? അല്ലേ ഇതല്ലേ കാണുന്നത്? Right. So I didn't know that such an option does exist. ഇങ്ങനെ വരയ്ക്കാനുള്ള ഓപ്ഷനുള്ള കാര്യം എനിക്ക് അറിയില്ലായിരുന്നു. I discovered it today. ഇത്രയും ക്ലാസ് കഴിഞ്ഞിട്ടാണ് ഞാൻ കണ്ടുപിടിച്ചത്. Right. So that is I never right clicked the things. So you had say these are both using shortest path trees, only the metrics differ, right? So as mentioned, you have the forwarding table. So you have the table like this. Initially at boot up, this is a situation. It knows the cost. നമ്മൾ നേരത്തെ കണ്ട എക്സാമ്പിൾ തന്നെയാണ്. N4 reach N12, it shows the cost. Now how updates happen, that's what we discuss. Say updates happens is that updates have to happen, and by exchange of this link state data packets, and then we'll just compress the entire thing, whatever mentioned for link state packets, that has to be done. Link state packets exchange, you will have to update the cost, and each will use this Dijkstra's algorithm to compute the its shortest path to every other node. Now ഈ പ്രോസസ്സിൽ ചില റൂട്ട്സ് ഹയർ കോസ്റ്റ് ഇടാം, അഡ്മിന് തന്നെ ഹയർ കോസ്റ്റ് ഇടാൻ പറ്റും. അപ്പോൾ that comes in the next thing, but still we also saw that some routers may be avoided because of security reasons or other traffic reasons, something, because so you can give preference in the because all these interior routing protocols works in synchronization with the exterior router protocols. BGP updates നമുക്ക് കിട്ടും ഈ പ്രോട്ടോകോൾസിന്, അതനുസരിച്ചാണ് റൂട്ട്സ് തീരുമാനിക്കുന്നത്. These people, the interior router protocols cannot interior routing protocols cannot work independently of the exterior router protocols, so they have to work in synchronization. Those exterior or border gateway routers will provide updates to these routing tables, so that will be giving a vector picture of this. Now to prevent this flooding is creating a lot of traffic. To prevent such a thing, what is the idea here is that they will use something called as autonomous system sub areas. You will divide this, so this is a large autonomous system. You will divide it into small areas. Each will be assigned some number. So area 1, area 2, area 0, and there will be one area which is designated as a border or glue area. So this is called as a glue area, or which will so if you plan to flood this say the entire network with updates from link state packets what happens, that will create a lot of traffic in the entire network. So what it does is that it floods, each router will be flooding in its own area, and what is the summary that will be gathered by this area border router, and that will be passed on to the other areas. So this serves as a backbone area. Area 0 is having a backbone area. So that will restrict the flooding to some extent, because only the summary is passed on. Summary of whatever is happening is passed on by this area border routers to the neighboring autonomous systems. The link state packet exchange can happen within area 1, within area 2, area 3, like that, and each of them will be giving its updates via this area border routers to the backbone area 0, and that will be disseminating this information to the remaining areas. So you set up a hierarchy, sub areas. So you set up a hierarchy at a lower level, autonomous systems, and below the autonomous system you have areas. Okay, so so that is what we mentioned. So it's gluing these areas together, or the slide. So this is the basic concept. So this is the basic idea, right? Now this open link state advertise. There are 5 types of advertisements. 5 types of advertisements. So this is router link, network link, summary link to the network, summary link to autonomous system border router, external link. So such things. So you'll have to advertise link state packets. That's what basically link state advertisements. So we'll see different types of link state packets. Link state packets, these are say I'll just say this is one is called as a router link. You will advertise existence of a route. This is a router link. So the router is advertising. This is a point-to-point link. So this link is advertised. Then there is a transient link. Transient link is a network link, advertises the network as a node. So this is a node. So you will advertise. So this is this network is reachable by this route, like that way. So this is a network link. So different types. Then this is the what we discussed earlier, summary link to the network. This is done by the area border router. So this graph, this area border router is advertising. The summary is passed on to this backbone. That is what the area border summary link to the network. So from each of these areas, the area border router will pass the summary to the backbone area, so that it can be disseminated to other areas. Summary, only the summary goes there. Then summary link to autonomous system. So summary links from other areas. This link, whatever we saw here, this one, autonomous system boundary router, border router, that will be advertising the summary of whatever is there in this autonomous system to other autonomous system. That is the 4th link, right? Summary link to autonomous system. So that is the 4th type. And the 5th type is external link. So external link is has to do with there could be some networks which is external to the autonomous system, which is not part of this autonomous system. It is having some relation to this autonomous system, but it is out of the administrative domain of this autonomous system. So such networks are advertised using such packets. So maybe some entity wants to remain separate from this autonomous system, but needs to have some connectivity. So such advertisements are done using external link packets, link state packets. These are the 5 types of link state packets, 5 types of link state advertisements or link state packets. Link state packets are advertised in another, right? The different types. You can advertise as a router, network. You can advertise it as a summary link. And also summary link to the AS border router, like that. Summary link to the network means this is a border, area border router is advertising. This is to other routers. This is external. This is router advertisement, network advertisement. Then area border advertisements. Then other autonomous systems and external links. Simple കാര്യങ്ങളാണ്. പടമൊന്നും ഓർത്ത് പേടിക്കേണ്ട ആവശ്യമില്ല. This is, you have the mental picture what is happening. So network, router, network, area summary, and then autonomous system summary and external link notification, such things, right? Then it is implemented in the network layer, unlike your RIP. This is implemented in the network layer and uses IP datagram. So you have OSPF in the network layer, that is IP layer itself, and it will just set the value as 89. That is the protocol field in the IP datagram value set as 89 protocol values. So these are encapsulated within the IPv datagrams. There are two versions. OSPF version 2 is the dominant one now. So I don't like saying such things, but these are some messages to be descriptive things. We are not going to in depth, but if an essay question comes, you will have to write all these. I'll say, yeah, at any point a practicing engineer can refer things, but unfortunately the exam has to verify that you know something about this. So these are 5 types of messages are there. 5 types of messages. Hello message, it's introducing. You can say say database description message. So it is in response to hello message. You will send an update. Okay, from each, say router 2 is sending, when router 1 boots up and it sends a hello message, the router 2 will send reply back by using the database description message, sending whatever it knows. Link state request, you can request about a specific link, maybe the entry timed out in the home router, it can request like that. Link state update. So this is the key thing. That is what 5 types under the link state update messages are 5 types. Okay, these are the 5 types of link state update messages. This is a type 4 message. The other one is a hello, then response, then request a specific link. Then this is the 5 types we saw. Link state update, advertisements, and acknowledgement has to be there. Whatever router receives the update using this link state update message has to respond by an acknowledgement. Other registered post with acknowledgement, it has to be acknowledged that it has received this link state update message. The OSPF is a complicated protocol. So even though it is an open source, it is considering all such things to make itself very reliable. It's a complex protocol. But it is converging faster than routing information protocol. The only drawback here is that every router has to run this Dijkstra's algorithm or variants of that. Modified Dijkstra's algorithms exist. Different variants are there. Dijkstra's algorithm is the entry level, you can say like that. There are proprietary algorithms which are owned by different companies, say Cisco, Juniper, all those things. They have their own proprietary algorithms which will be running their, powering their routers. So OSPF is something, it's an open source thing which is there. So remember, even with all these heterogeneity in the network, the internet works very flawlessly, and we do hardly notice any problems. So we are unaware of all these inner workings. We just say net connection illennu maatrame nammal parayarullu.